Hello everybody and welcome to session 1 of Hydro 2020 on potential and planning. I'm Alessandro Palmieri, former World Bank lead specialist and now World Infrastructure Advisor out of Italy. To put in context the presentation that we'll hear, I have broadly divided hydropower projects in 3 groups. The first one, I call them transformational projects. Most of you are familiar with them. They are developed in developing countries the same way they were developed in last century in industrialized countries and are aimed at inducing major changes in national and regional economies. Then we have rehabilitation and upgrading projects. These are mainly taking place in industrialized countries which have developed their stock of infrastructure and try to get the most of the existing one and also prolong their life. And the third group is something that is showing recently, although not yet has attained general attention, and are new storage, new supply side projects in industrialized countries for much neglected development for a long time. We are seeing this happening more and more frequently in industrialized countries. So with this kind of classification in mind, I have tried to locate the 5 contributions that we have in this session in this triangular diagram in which you have transformational projects, new storage, and rehabilitation and upgrading. And you see that they nicely spread along this area. And we will hear from the presenters and we'll try to promote a good discussion. And finally, I want to point out that there are other sessions in Hydro 2020 which are relevant to the subject of potential and planning. Session 3 on cross-border collaboration, session 20 on pump and storage technology, and session 40 on sedimentation management. And the reason, the relevance of this session is quite clear and is shown in this table. So look forward to an interesting session and let's get started on that.
Good morning, and thank you to the organizers of Hydro 2020 for inviting us to give this session's keynote talk on new hydropower opportunities enabled by the co-design of river basins and power systems. My name is Julian Haru, and I'm joined by my co-author, Dr. Matteos Pantelli. We're both at the University of Manchester in the UK. This work was funded by a UK research project called Future Dams. And Future Dams stands for Future Design and Assessment of Water, Energy, Food, Environment Megasystems. Its website is futuredams.org. Future Dams has 4 case studies in West Africa, East Africa, the Middle East, and Asia. So you can imagine by co-design of water energy systems, we're talking in some fashion about integrated water energy systems. Indeed, water and energy are typically managed and planned separately by engineers and planners. And that's also reflected in the mathematical models that are used to manage and plan those systems. For example, power systems models often treat hydropower as a fixed input, and water system models often allocate water to hydropower generation without considering energy needs of the system. So the temporal and spatial synergies of water energy system are simply not considered in the tools that are used to manage and plan water and energy systems. So our question is simple: are there benefits to an integrated approach? This integrated approach has 3 steps. The first is to simulate spatially the water and energy system. And that means simulating the water system, the energy system, and their joint interactions. And when we do that, not only track those flows, but also track the engineering, service, reliability, environmental, and economic performance metrics that go along with them. The second step is search, also called optimization, where we're going to try to find the most efficient designs, water energy designs, and operation modes, and the trade-offs that those imply. And you'll see with the results later what we mean by that. The third step is to deliberate, or to collaboratively and interactively assess those trade-offs and help make decisions. Okay, let's look at some of these methods and these simulators. So very quickly, the one that we use for water resource system simulation is called PyWR. It's open source, it's free and open source. You can get it on the internet. It's very fast and it's a generalized model. It links to multi-objective optimization, which is the search algorithm or the search technique that we use. And generally this enables applying advanced river basin simulation on real systems with, for example, a weekly or monthly time step. And there's a paper below there if you're interested. The energy system simulator is built with a similar tool. It's a fast generalized spatial power system simulator. We've yet to publish this one, but that'll come. It also links to the search. It can simulate in sequential, chronological, or non-sequential simulation. So you can do things like hourly time step, or at a more abstract level, simulate things like representative days. And it can also simulate the unit commitment in power systems. Now, how do we join those together? Well, we use an integrated object-oriented software framework that we built a few years ago called PNSIM, which stands for Python Network Simulation Framework. And that allows each model to stay independent but connect at runtime, so while the models run. And this enables multi-directional interconnections between the systems to be simulated. And there's a paper there that details how that works. The second step of the approach was search. As you can see here, it's a multi-dimensional search. So the way that works is, imagine you were buying a house and you value distance to work and cost. And if you plotted all the houses on the market, you can see here that this red line of points is showing for any distance to work what the cheapest house is. And an engineer would call that the non-dominated front, or an economist the Pareto optimal front, or it could also be called simply the best houses. And this is the technique of optimization that we use in this project. Okay, an application. We've applied this recently to the Intertide National System of Water and Energy in Ghana. Ghana has some challenges. There's generally an increase in water and energy demand due to development. There's potentially quite a bit of solar potential, but it's especially in the north. The problem is that the demand is especially in the south. That's where the higher energy loads are. And you can see there the water system and the power network in black that we simulate with the simulators. So our challenge here is simple. The challenge we set ourselves is how to meet future energy demands while producing less emissions than today, and hopefully also lowering costs and increasing service reliability. And so for that, we're going to set up a design problem. The decisions of our problem are where to expand solar. So in which of those grid cells on the left map, where to expand the transmission lines, if at all to expand the thermal generation, and what are the operating rules of the hydropower reservoirs which allow the system to work. And the objectives of the multi-objective optimization problem are listed there. You can see that we're going to be minimizing costs and energy demand unmet. We're going to be maximizing hydropower and firm yield and water supply reliability, for example, to agriculture, and including maximizing flood recession agriculture. Let's look at some of the initial results of this design problem. On the y-axis, we have the emissions reflecting how much thermal is generated. And as you reduce that, it's because you're producing more from solar. On the x-axis, we have the hydropower energy produced. And the color is the firm yield generated by hydropower. The reason why we're not seeing a crisp two-dimensional Pareto frontier is that we have 8 optimization objectives, yet we're looking at this space in 2 dimensions spatially and 1 with color, so 3 dimensions. And that's why many of the points are overlapping. But what we're seeing here is an efficient frontier. So all these points are of interest. To simplify the interpretation, we've tried to keep most of the other benefits roughly equal, but to pick a point on the left side with 450 megawatts of firm hydropower, and on the right side, the green point, with 225 megawatts of firm hydropower. And what these 2 clusters of points and the 2 selected points show is that there's really 2 ways to operate your hydropower. The purple point is an example of historical operation where hydropower is used for firm power to generate base load. And the green point is reoperated hydropower, or hydropower that is specifically designed to enable solar generation. And you can see to support solar. And you can see here that that results in 6% less emissions nationally. So let's look at those same results, but in a different format. On the left side in panel A is the historical operation, so the purple point. And on the right panel, B, is the reoperated hydropower designed to support and enable solar energy production. So you can see that, first of all, to explain the plot, what you're looking at here is 24 hours on the y-axis over a 3-year period plotted on the x-axis. So each thin line is 1 day. The panel A has considerably less solar, less hydropower, and more thermal than the reoperated hydropower in panel B, which has more solar, 6%, 2% more hydropower, and 8% less thermal, which results in that 6% reduction in emissions. Same data as the last slide. What's interesting about the plot is you can really see the mechanism of how that happens. If you look on the right side in panel B, you see those lines of blue in the middle of the day. So in the daylight hours, you have those blue squares, which are periods of low hydropower generation. And what that's doing is it's showing you how the integrated simulator is seeing the solar availability during the day on a daily basis and switching between hydropower and solar so that it can save water, save the hydropower, and generate during the day with solar power whenever it's available. Here are the same results, but plotted in a different way. Now we're looking at the generation coming out of Akosombo Dam, Ghana's major reservoir. The orange is the historical baseload operation of hydropower, and the blue lines are over a 3-year period the generation resulting from the reoperated solar enabling hydropower operation. What we can see here is that there's considerable negative hydroecological impact if we purely manage the reservoir releases only to enable solar. The change in the hydropower operation to follow load increases downstream hydrological alteration because of hydropeaking. So there's a trade-off between hydro-enabled solar generation and hydroecology that we still need to look into in further research. In summary, we can say that hydropower allows moving water in time to respond to changes in the net load and solar availability. Such hydropower reoperation enables more solar and less thermal generation and reduces CO2 emissions. In our case, in Ghana at national scale, was about by 6%. However, so far we've seen there's an emissions reduction, hydrological alteration, or hydropeaking trade-off that needs to be considered and further looked into. Thanks, that's the end of the talk. This is just a screenshot of the software. So what's neat is that the simulators are open source, but they're also available on the internet for free. So this is just a snapshot of what the system looks like when you actually use it on a website. Here are the Future Dams researchers involved and practitioners in this Ghanaian case study. The lead technical authors for the study were Jose and Alex, featured in the middle top. And we also see that we had many collaborating partners from various institutions in Ghana. And here is the early publication that summarizes the design framework. It's available in open access.
Good morning, everybody. My name is Sebastian Sterrel from the Faculty of Engineering of the Free University of Brussels in Belgium. And in this presentation, I'm going to show you the results of our recent research advances on hydropower as a catalyst for the uptake of solar and wind power, with two specific case studies from the developing world. To give you some context, hydropower, as many of you will know, is the most used renewable electricity resource in the world, but solar and wind power have been making tremendous advances in recent years with unexpected and unprecedented growth rates. Now that is good news for the climate, but comes with its own challenges because these resources are variable and fluctuate depending on the weather from minute to minute, hour to hour, and season to season. Hydropower has often been presented as a way to compensate for these variabilities thanks to its flexibility of dispatch. Now, in theory, that's a quite straightforward thing to think about. The schematic on the left here shows you how hydropower, or a fleet of hydropower plants, if you will, could provide both baseload power during a certain time period, as well as the peaking power needed to compensate for, let's say, the absence of solar power during nighttime or the intermittency of wind power in order to carry a certain load. So hydropower can function both as a baseload as well as a flexibility provider. Now, that on the face of it, that may seem like a relatively simple thing. Just adapt the operation of hydropower plants according to the availability of solar and wind and according to the demand, and you're there. But it's not that simple. It's about more than just considering the hourly weather patterns and adapting hydropower plant operation in function of that. Because in reality, you'll need to consider a whole range of other scales and problems to do this in a proper way. For instance, you'll need to consider also the impact of seasonality, of rainfall, of river discharge, but also of solar and wind potential on the management of hydropower plants and their flexibility, as well as the climate change signal, which pans out on decadal timescales. Moreover, it's important to consider the environmental flows that hydro reservoirs have to guarantee in order to safeguard ecology downstream, as well as the multi-annual management strategies of reservoirs to safeguard lake levels. So quite quickly, this can become a relatively complicated problem that requires a lot of data in order to be analyzed properly. So in the department where I work, we've developed software tools to do this, and I'm going to show you the results of two specific case studies that we've carried out, which consider all of these timescales and problems in an integrated manner. And the two case studies I'm showing you actually span a wide range of grid scale relevance. And they're in fact both from opposite ends of the spectrum of the size of the grid we're considering. The first case study is from an isolated island grid case, a grid that stands on its own without interconnections to other countries in a small island developing state. The second case concerns an interconnected power pool strategy across an entire subcontinent. The first case study is from the South American nation of Suriname, as I said, a small island developing state. The second case is from West Africa in the context of ongoing efforts to integrate national power grids into a joint West African power pool. Let's start with Suriname. Suriname is a small country along the northeastern coast of South America, which has historically relied on a mix of hydropower from a single big hydropower plant and thermal power from several diesel-powered plants. The main grid of Suriname, which serves the capital, Paramaribo, is isolated and has no interconnections to other grids. The hydropower plant was originally developed to benefit the aluminum industry, but as this industry declined, the plant was handed over to the Surinamese state at the end of 2019. So Suriname now has a new old hydropower plant in its possession, which could be put to use to benefit a clean energy transition. In collaboration with the National Utility Company of Suriname, we looked at the potential for using the hydropower plant, leveraging its flexibility to develop coastal wind power. The coastline of Suriname receives strong trade winds during part of the year, and most of the population lives there, so the transmission grid is already present along the coast. There could therefore be interesting ways of using the hydropower plant to develop coastal wind power. In this context, it's interesting to note the complementarity between the wind and the hydro resource in the country. Wind speeds blow strongest during the dry season at the beginning and the end of the year. Obviously, the hydropower potential is highest during the wet season when the reservoir refills. So we have a very clear case of a seasonal hydro-wind complementarity here, which could be leveraged to benefit the introduction of wind power on the Surinamese grid. Here I show you model results of how the operation of a mix of hydro, wind and thermal power to meet Surinamese demand could look like from hourly to seasonal to multi-annual scales. Now on an hourly time scale, our model suggests that the hydropower plant should be dispatched in certain ways, depending on the availability of wind and the total demand in order to displace thermal power from the mix. Now, if you keep that operation across the year and across several years on end, then on a seasonal timescale, you'll see that you reproduce exactly this complementary behavior, with wind power reaching up to 50% penetration during the dry season and hydropower taking up the baton during the wet season. And on a multi-annual timescale, we see that the hydropower plant is even capable of compensating for interannual variability in the wind resource. So after doing some economic analysis on this, we find that hydro-supported integration of wind power is economically advantageous up to around 25% of wind power penetration on Suriname's main islanded grid, which together with hydropower would mean roughly 80% renewable and clean electricity supply for the country. The second case I'm going to show you now concerns a whole other scale of grids, namely interconnected power pooling across an entire subcontinent. The aim of this research was to look at how the ongoing efforts to integrate countries' national power grids into one regionally integrated West African power pool could best be harmonized with the need to deploy more and more clean energy projects from solar and wind power in the region to reduce the use of polluting fossil fuels, and how this could best be harmonized with the potential flexibility of the existing and also the planned hydropower fleets across the region. So we used the same modeling approaches as we did for Suriname, but instead of applying them to one single hydropower plant and one single type of wind power project, we actually looked at the entire subregion and simulated the joint operation of all existing and planned hydropower plants alongside all upcoming solar PV and wind power plants in the region to clarify how a regionally integrated power grid could benefit high penetrations of solar and wind power and the deployment of flexible hydropower. And in this case, we saw that there were a whole lot of other synergies and complementarities that had to be considered. In the Surinamese case, we have one type of synergy, seasonal, between two types of resources, hydro and wind. In this West African case, there's a whole other range of synergies to be considered. We've got a seasonal synergy between hydro on the one hand and solar and wind on the other, with solar and wind power strongest during the dry season, hydropower obviously during the wet season. We've got a diurnal synergy between solar on one hand and wind power on the other. Solar power obviously available only during daytime, but wind power potential actually being highest during nighttime in West Africa because of low-level jets that blow at the hub heights of wind turbines. And lastly, we've got a spatial synergy between the north and the south of the region, with hydropower potential being mostly concentrated in the wet south, which receives the most rainfall, and solar and wind power potential being strongest by far in the northern part, the dry part of West Africa. So we could say that we are dealing here with a case of multi-scale spatio-temporal hydro-solar-wind complementarity. We find that if countries were to plan their own contribution to a regionally integrated power grid, according firstly to their own nationally available resources, but secondly also to the way that these resources would harmonize with those present in other countries, then a picture like shown here on the right hand would appear, with most countries in the south of West Africa contributing a lot of hydropower, all countries contributing an important share of solar power, and some countries in the north contributing most of the wind power. So a mix of renewable electricity resources with roughly 50% hydropower and 50% VRE, which we find could meet more than 60% of current electricity demand in West Africa if countries could share these resources on an integrated power grid. So a regionally integrated power grid allows for efficient leveraging of VRE potential, and therefore we would support that such considerations are taken up in the ongoing planning towards the West African power pool. We find that existing and smartly planned new hydropower can play a strong role as a guardian of the grid in order to safeguard grid stability and compensate for solar and wind power variabilities. And for all of that, integrated resource planning of solar, wind, and hydro together is crucial. We also find that with the expected drop in costs of solar and wind power across the next decade, such strategies may become cheaper than the status quo in West Africa, which is mostly a combination of hydro and thermal power. And we believe that this would constitute an extremely interesting case in the framework of planning power grids from the start based on the idea that they should be designed for renewables, which is an opportunity that Europe and the United States have never had. This would be an opportunity for West Africa to leapfrog the age of fossil-based, large-scale integrated power grids in order to plan for power grids that are designed for renewables from the outset. If you're interested in reading more, then I can refer you to the two publications, the first one on Suriname, the second one on West Africa, that we've published during the last year. We've got work on other regions ongoing, notably the East African Power Pool, but also others. If you'd like to know more or have any requests for further information, feel free to contact me by email or through any other means. And obviously, I'm happy to receive your questions during the session hereafter. Thank you very much.
Good morning, my name is Anya Becker and I'm from the University of Pretoria in South Africa. Today I will be presenting on the development of a tool to identify hydropower potential at pressure reducing stations in South African water supply and distribution systems. Just a brief overview of the presentation. First, I will provide you with some background information to explain why this study is necessary. An introduction to conduit hydropower, as well as some examples of conduit hydropower plants in South Africa will be provided. And then finally, I will discuss the proposed methodology for the development of a conduit hydropower tool, with a brief discussion of the conclusions. There is a shift towards harvesting energy from renewable sources as the price of electricity generated from fossil fuels and the pressure associated with reducing energy-related carbon emissions are increasing. So introducing renewable energy as a form of energy generation can result in both the reduction in pollution as well as the mitigation of climate change. And hydropower, especially small hydropower, is an ideal solution for developing countries such as South Africa to supply electrification to isolated communities and to assist in peak supply. The challenge with hydropower development, however, is during the planning phase, as the lack of access to available water infrastructure restricts the quantification of hydropower potential and thus the identification of potential sites. So this study aims to alleviate the problems associated with challenges when limited data is a problem through the development of a hydropower evaluation tool. But in this presentation, however, I will only discuss the development of a conduit hydropower evaluation tool. So just a brief introduction into conduit hydropower. Water distribution systems often have hidden potential for hydropower generation at pressure-reducing stations, where excess pressure can be utilized for energy generation instead of being dissipated. The utilization of the excess pressure can be achieved by either replacing the pressure-reducing valve with a turbine or by installing a turbine in parallel with the existing PRV. South Africa has some existing conduit hydropower plants, of which some examples include the Pier van Ryneveld plant with an installed capacity of 14.9 kilowatts, the Brandkop Reservoir with an installed capacity of 96 kilowatts, and then the Anden Reservoir with an installed capacity of 150 kilowatts. So the remainder of this presentation describes the proposed methodology for the development of an evaluation tool. And as mentioned previously, the aim is to assist in the quantification of a first-order estimate of the hydropower potential available at pressure-reducing stations or break pressure tanks, especially where restricted access to data is a challenge or poses a challenge. So there are 5 steps included in the proposed methodology, but only the first 2 steps will be discussed during this presentation. The first step is reviewing existing data or existing studies describing the evaluation of conduit hydropower. And then the second step is finding suitable methods of estimating flow and pressure head when limited data poses a challenge. So these studies listed are some of the selected studies on the evaluation of hydropower potential at break pressure tanks and pressure reducing stations that were assessed with the aim of finding existing methods of evaluating hydropower potential in water distribution systems. So even though quite a few studies were found that described methods of evaluating hydropower potential in water distribution systems, there was a general lack of studies dedicated to the quantification of hydropower potential or hydropower parameters using limited data. So this brings me to the next part of the methodology, which is finding suitable methods of estimating parameters. As I mentioned in the previous slides, there aren't any studies that have been dedicated to finding methods of estimating parameters when limited data poses a challenge. So the aim of this step is to make certain assumptions or apply certain criteria to be able to estimate the parameters necessary for hydropower potential quantification. And in the case of conduit hydropower, the 2 parameters that need to be estimated is flow and pressure head. So first, I will discuss a suitable method of estimating the parameter flow. So if hydropower potential quantification is required and the flow parameters are known, there are 2 ways of estimating the flow. The first is to assume the flow to be equal to 55% of the PRV size. This value was obtained during a study to find the relationship between the PRV size and the flow through the PRV using the data from a number of South African reservoirs. Option 2 is to assume the flow velocity in the pipeline to be equal to 1.5 meters per second. There are, however, some limitations to this. What happens if you have a more complex system? So, for example, if you have 2 reservoirs, but they aren't connected with a single pipeline, there might be multiple pipelines between the 2 reservoirs, or if you have some flow abstractions or even some incoming lines along the system. And next is to find suitable method of estimating the parameter pressure head. So during the estimation of the parameter pressure head, 5 scenarios were considered. The first scenario is where basically all your parameters are known except for your pressure head. So the location, static head, length, and the diameter of the pipeline, they're all known. Scenario 2 is the scenario where only the length of the pipeline is not known. That is the difference between scenario 1 and 2. Scenario 3, only the location and the diameter of the pipeline system are known. Scenario 4, only the static head of the pipeline is known. And then scenario 5, no information is available. So let's first look at the pressure head estimation of scenario 1 and 2. Scenario 1 is quite simple. All the parameters are known. So the pressure head can be calculated by subtracting the losses through the system by the static head. And scenario 2 follows the same path, but the length of the pipeline is unknown. So the proposed methodology for finding or estimating the pipeline length is to obtain the direct length between the two scenarios, the length A, from a digital elevation model of South Africa, and then applying a correction factor to get the estimated length B. After which the pressure head will be calculated using the same formula as scenario 1. Now for the pressure head estimation for scenario 3 and 4. Scenario 3, the location and diameter are known, but the pipeline length and the static head are unknown. So the length has to be estimated first using the process as described in scenario 2, and the static head can be estimated or can be quantified if the elevation difference between the two natural ground levels of the reservoirs are known, as well as the reservoir levels. So to get the elevation difference between the natural ground levels of the two reservoirs, a digital elevation model can be used if the locations are known. Once the estimated length and static head have been quantified, the pressure head can be calculated using the same equation as in the previous two scenarios. Scenario 4 is where no data except for the static head is known. In this case, the pressure head will be estimated as 70% of the static head. For scenario 5, no information is available, so in this case, no pressure head estimate will be made. The proposed preliminary methodology is presented here in the form of a flow diagram. The flow diagram requires some input information and eventually will lead to the quantification of the potential available and whether the potential available is considered to be enough or whether the site under consideration should be excluded. So all the criteria as indicated with blue still needs extensive research to either quantify some of the correction factors or criteria or to validate the criteria even further. So this brings me to the conclusion of the study. A conduit hydropower evaluation tool is being developed to assist in the quantification of hydropower potential. And the first steps in developing such a tool were finding methods of estimating the flow and pressure head when limited data poses a challenge. So this tool is still in its infancy phase of development, and a lot of the criteria and assumptions still need to be validated, but it is believed that such a tool can assist with the quantification of hydropower potential, especially when limited data poses a challenge. And currently, the data of 10 additional sites are being analyzed to find some of the correction factors that have not been found yet, or to even to validate some of the criteria that have already been included in the framework. And this is the end of the presentation. Thank you for listening. And I want to say thank you for the Water Research Commission who funded this project.
Hello to everyone, and thank you for your interest in this presentation. My name is Pedro Diogo Pinto, and today I'm going to talk about how to identify the best optimization opportunities in a hydropower plant portfolio, the EDP method. This is our agenda for today, and let's start with the introduction. The aging of power plant portfolio and with fewer investment opportunities in new power plants, utilities like EDP are getting more focused in optimization strategies for their assets. Having said that, we know that within a power plant portfolio there are different types of power plants with different scales, technical solutions, market exposure, hydrological conditions. So it is challenging to identify the best optimization opportunities. We also know that different optimization strategies will have different impact both on investment costs and future revenues. Hydropower plants are also in competition with other technologies such as solar and wind power. And with this, we know that it is mandatory to put our effort in the best optimization strategies. So EDP has created a tool that helps us to decide which projects are the best ones and which are not. And so we will focus just on the best ones. We have called this tool ranking. The ranking, it is a tool that uses databases such as MIBEL prices, operational data, investment costs, prices forecast to produce indicators that will help us to decide the best projects. These indicators are the ratio between internal rate of return and the cost of capital, a global evaluation, the net present value, and the project risk. To calculate the indicators, we would say that we need 5 steps. The first one is the project description. Then we have the introduction of the investment costs, the intervention period, the estimated optimization, percentage or power, and the quality assessment. After that, we have the algorithms. The algorithms will update the databases, will calculate the indicators, and finally, we will have the ranking of the projects. Moving next, we have the project's feasibility, data, and methods. Here we have the 4 databases. The first one is the MIBEL prices, and the MIBEL prices are coming from a market operator for Iberian Peninsula, which is OMIE. We use the day-ahead data. This is hourly data since 2010. We have a weighting factor that puts higher weight in the recent years. Second database is the operational data. It's an internal database. We use data from the last 5 years. We consider that the last 5 years are appropriate for this kind of analysis. We use variables such as head, flow, and power. And once again, we use early data. Then we have the prices forecast. We have 4 different scenarios and prices until 2100. Finally, we have the investment costs. It's a historical database from previous investments of EDP, and we also use suppliers' information. The next step will be to estimate the yearly output increase, and we have here a general equation that helps us to define the yearly output increase. We use the data from the last 5 years in terms of production. We multiply each hour by a price within the price matrix. The price matrix is here on the right. I will explain with more detail this price matrix. And finally, we multiply it by an estimated output. So the price matrix has 24 hours and 12 months. So this means that we have a price for each hour within a month. This price matrix is created with the data from MIBEL, the last 10 years, like I said before. And this is, we consider this as average prices. As we've seen previously, the estimation for the yearly output is defined for the initial moment. For the following years, we need to update them according to perspectives on prices. For that, we have 4 different scenarios marked here on this graph. The official scenario in terms of comparison between projects inside EDP Group is the energy outlook conservative. We have also 3 other scenarios. The yellow one, which is a constant evolution of prices. The red one, which is based on forecasts of future generation, and another scenario that is the average of the last three scenarios. This data shown here is for demonstration purpose only. This is not real data. And we are able to select which scenario we want to have for our simulation, and our indicators will be calculated based on the selected scenario. Every project under analysis will have a detailed report with a description of the project and other relevant data. We have classified this data according to three different categories: revenues, investment and losses, and quality indicators. For the revenues, we have the type of optimization that we want to implement. I will address to this later. The expected optimization increase, the new minimal and maximum power of the unit, and the number of units to be optimized. On investment and losses, we have the investment costs, the project development time, and the outage time. These will have impact on losses due to outages. The quality indicators, we have environmental and stakeholder restrictions, equipment status, and exploration restrictions. This is a scale that we have to select. It is a scale between 0 and 1. Regarding the types of optimization strategies, we have developed until now 10 different algorithms for each one of the strategies listed here. As an example, we have here the pump efficiency increase, and as I have said before, the algorithm is based on the general equation. So, for the pump efficiency increase, the yearly output increase is calculated based on the hourly production of the last 5 years, multiplied by electricity prices from the price matrix, the estimated pump efficiency increase, the turbine efficiency, and a ratio of the pump consumption and the turbine generation over the last 5 years. And going next to the results. As we have seen before, we have 4 main indicators. The first one, the ratio between internal rate of return and the cost of capital. We will consider only projects with ratios higher than 1.4. The global evaluation, it's an indicator that uses an economic indicator, a time indicator, and a qualitative indicator. And we will choose the projects better classified with this indicator. The net present value, we will choose projects with higher net present value regardless the payback time. And finally, we have the project risk. This is a relative assessment method where we will compare the investment costs with the average investment costs of a group of projects. The same for the revenue losses, the same for development time, and the same for the remaining concession time. The investment project is planned. We calculate the net present value over the years, and we expect that in the end this value is positive. We also consider all undone cost savings and also operational costs. This is our ranking of projects in terms of these 2 indicators, and as we can see on the left, the ratios higher than 1.4 are marked within the red square, and on the right side, on the global evaluation indicator, we have also the best projects marked with 2 or 3 stars. Finally, we have the project risk, and this is our current ranking in terms of project risk. For the final remarks, we would like to say that this framework has the purpose of simplifying the preliminary project feasibility analysis. This ranking forecasts both costs and future revenues. To evaluate the feasibility of the projects, we have into consideration the net present value, the ratio between the internal rate of return and the cost of capital, the project risk, and a global evaluation of the project. Projects with ratios higher than 1.4 are preferable, and for the time being, we have on average net present values of 6 million euros for our projects. One project of 1 million euros has been developed. We also know that there is still margin for further improvements related to the other types of optimization projects. We also know that the allocation of the investment costs, revenues over the years may be perfect to allow a more accurate calculation of the financial results. Lastly, I have to say thank you very much for your attention, and these are my contacts. Thank you.
I'm Özgür Beşer from Tractable Engineering, Germany. Today, I would like to introduce you in-house developed software tool, EVALS. With EVALS, you can rapidly evaluate a large number of hydroelectric projects and their corresponding alternatives. The development of EVALS had started at the end of 1970s, and it is still a going-on process. The recent version is a major update with which EVALS abilities have been improved and extended with the integration of current developments in information technologies. For master planning, EVALS can be used for rapid site assessment and to define and refine key project parameters at an early stage. EVALS can be run for site selection and assessment of general layout alternatives during pre-feasibility studies. EVALS can determine key layout aspects and pre-optimize specific structures for feasibility studies. The application of EVALS in master plans, pre-feasibility studies, and feasibility studies significantly improve the efficiency of the engineering services. The identification, development, and comprehensive assessment of candidate hydropower schemes requires a systematic, yet time and cost-effective approach. To ensure the compatibility of results, costs, and benefits for individual candidate projects must be based on standard design criteria, as well as on standard procedures for cost and benefit estimation and project evaluation. For each candidate site, design of principal project elements is required. The planning engineer has to determine project installed capacity and calculate annual production. The cost for each element, total CAPEX and OPEX, has to be calculated. The planning engineer has to compute the net present value and benefit cost ratio. The decision makers should find answers to the following questions for each candidate site. What are the possible layout alternatives? Layout on the left bank like alternative A or right bank like alternative B. Select penstock or pressure shaft. What will be the dam type? RCC, rock-fill dam, earth-fill dam, or concrete gravity? Where should we locate the dam access? What will be the dam height? For each alternative, what is the optimum installed capacity? Will it be a reservoir, runoff river, or peak runoff river type project? Finally, which alternative to select for each candidate site? Afterward, candidate sites should be ranked so that most promising sites to be selected for the short-term, mid-term, and long-term investment plans. The latest version of EVALS is a standalone GIS-based desktop application developed for Microsoft Windows operating system. It is user-friendly and intuitive, so you can quickly focus on engineering. It dramatically streamlines your workflow. It can be easily integrated to existing decision support systems. Its plugin architecture allows to extend its application range. With recent version of EVALS, you can prepare layout inside its standalone high-performance GIS engine, with which you can also read and write more than 100 different formats. You can place more than 20 different common hydropower elements, such as dams, spillways, weirs, cofferdam, diversion tunnels, headrace tunnels, forebay, surge tank, penstock, pressure shaft, powerhouse, transmission lines, and extra. You can create different layout alternatives for a project. The recent version of the EVALS, with the GIS engine at its core, has a comprehensive set of streamlined terrain tools such as 2D profile extraction along with elements, excavation cross-sections definition based on baseline and catch line parameterization. As you can see in figure, you can define catch lines with benching and dynamically see the results on screen. Cut and fill calculations can be done on defined excavation cross-sections. Some other terrain functions are automatic basin delineation for a selected point, automatic river network creation with Strahlen numbers, calculation of hypsometric curve for a basin, calculation of reservoir boundary and capacity curves. Dimensioning of elements is achieved by applying parametric design approaches. Design parameters are stored inside an engineering library where each parameter can be modified and designs are simultaneously updated accordingly. Hydraulic calculations such as flood routing, water profile, and water hammer calculations are run wherever necessary. Accurate bill of quantities are calculated with the help of constructive 3D solid modeling approaches, which also creates an interface to CAD and BIM. Users can visualize designs on the fly in a 3D environment. Here you can see a design dam with an integrated spillway over existing ground and excavation cross-section in 3D. EVALS cost estimates are based on unit prices defined within UCOST database. The unit prices are the outputs of built-in programmable cost functions, so it is easy to update UCOST to different regions. During a run for selected alternatives, EVALS can optimize diversion utilities, dam and spillway complex, and power elements. EVALS performs reservoir operation calculations to determine peak and off-peak power, to compute firm and secondary energy using head discharge turbine efficiency curves, to maximize the value of energy while satisfying downstream water demands, to indicate minimum, average, and maximum filling times. EVALS has separate outputs and reporting interface where you can export results to common formats such as Excel and CSV. For each element, detailed BOQ tables and calculated design parameters are reported. Some other standard outputs are optimization results details, reservoir filling and operation simulation, and preliminary probabilistic economic and financial analysis. As a summary, EVALS is a GIS-based design and decision support system that streamlines the economic assessment, technical definition, and the identification of alternative layouts. Thus, it helps to optimize potential hydropower projects. EVALS enables the planning engineer to spend less time on tedious calculations and reporting and put more focus on his creative conceptual work and adding value to the project. Thank you for your attention. You can contact me directly by telephone or email.
Dear ladies and gentlemen, dear Alessandro, dear participants of this session of Hydro that is online this year, I'm glad to welcome you, and I want to present the topic that is shown on the screen. I will not read it and will just proceed describing the contents. In this presentation, we are trying to cover three topics which are rather hard to combine and also that are quite wide and general. These three topics are pre-feasibility studies and automation of those, estimation of hydropower potential and search for the potential sites for hydropower. The second one is, let's say, the next stage when a good site is selected and one needs to proceed further to study the watershed further, to provide the update of the estimate of the inflow and of the generation of the potential hydropower plant. And the third phase is that when the construction is ongoing and the models are made even more detailed to do the detailed forecast of inflow for operational purposes, and also when the system becomes more like a monitoring system. If we start with the hydropower potential, on this slide you can see what is understood under hydropower potential, what is available hydropower potential, and what you can technically use, and what is economically feasible. Hereby you may see how the algorithm to estimate hydropower potential actually works. It consists of collection and processing of data of two types. One is trained data that allows you to create so-called synthetic rivers, and these are mathematical acquired rivers that would flow if you just consider the digital elevation model and how the water would follow this terrain. The second set of data is related to hydrology, and the regular approach is so-called runoff module maps, which has a characteristics of liter per square kilometer of liters per second per square kilometer of the watershed area, with the annual figure of discharge for these characteristics for area. So we've developed it a bit further, but I don't have time to stop here. So using these two types of data, you analyze river segments section by section and then go from up to down to calculate what is the gross hydropower potential. So after you've calculated the so-called gross hydropower potential, it is also important to understand where you can use it. So depending on the territory, these criteria could change, and for Russian territories, what we've applied was analyzing which territories are national parks and other ecological restricted zones, where you already have hydropower potential used, like reservoirs that have already been created, or some territories that are extremely unfavorable for geological conditions. So having this data, you may select the synthetic rivers or mathematical rivers and subtract them from further estimations. So this allows you to calculate the automatically calculate the available hydropower potential. What is also important is verification of results. So when you have your mathematical model and you have some estimation of characteristics of the rivers, it is important to compare the results with the previous studies so that you find some errors, if any, in advance before proceeding any further. So we have analyzed, as I said before, about 10,000 rivers in Russia, and we've also published some articles about this study, and generally the results were very close in terms of catchment areas, were a bit less close in terms of estimation of flow, and varied, let's say, up to 20–30% in estimations of hydropower potential. But hydropower potential itself and also available potential, these are just figures. So what is important is to be able to find some good sites, some good places on the river that would be favorable for hydropower construction. In fact, it could be not only hydropower construction, it could be water storage dams, or it could be pump storage, or it could be multi-purpose water storage dams. So, of course, the purpose of usage, it dictates what criteria you will analyze while searching for the good site. So this is some criteria we have been using for our search of small hydropower plants, and we were using the same parameters to narrow the search further, to have some filters in our system. Hereby you can see how the described method works. So for a small basin, you have a set of rivers which are subdivided into small sections, and then each section is analyzed for variance of hydropower plants. And then this section is finally, the list of these sections and variance is narrowed by applying to those a set of criteria. So here with the 98 stream reaches in the beginning, we come up to 20,000 plus variants of hydropower plant sites, and then we narrow the search to 36 variants of sites that can be analyzed one by one. In order to apply the described methodology, of course, you need some initial data. Here is the list of the data that you need to collect in order to make these tools work. And more or less the same list of data we've managed to collect for not only Russia, but also for Cuban territory, and the method actually worked quite fine. So you start from the terrain data and runoff data to provide possibility to estimate hydropower potential. And then you add restriction areas to narrow your search where you cannot build for sure. And then you add infrastructure to locate the sites close to cities and possible consumers. And also you will need, of course, river network and water use zoning maps, because this is our field where we are working. So to develop all the above, we found it practical to use a geographical information system which is server-based, and to create separate applications for specialists of different field. And then using these applications, the specialists, they work on their own data, but then this data becomes available for everyone else, and this creates a huge synergetic effect. So when you need to proceed further, and you already have some sites found, we start to cover, let's say, our recent experience, and what you need is to analyze your watershed more precisely. You need to analyze the catchment area, and in our case it was watersheds in mountainous areas with snow and glacier melt, and here there are quite a lot of modern products satellite based to supply you and to create further models to know precisely, let's say, what could be the distributions of flow within the year, what you could expect annually, and this allows you to create more precise estimation of the future generation. And also what is quite interesting is estimation of reservoir volumes. We have compared recently what you can achieve from, let's say, some maps dating back to 1970s, which were used in the previous stages, and then these new satellite-based, radar-based digital elevation models. So we have compared those, and it is quite interesting results for volume estimations of the future reservoir. So we'll try further with this very general topic, but as soon as your site is found and the construction is about to start, you basically want to know a bit more about the basin to make sure about that your estimations were correct, and what you want is to collect more data about the basin. So what is important here is to understand what gauging sites you had with the years of operation, which sub-basins you consider are not studied enough and you want to install some new sites there. And also the weather stations, where is the area, let's say, in terms of elevations that you don't have enough data, so where you want to install some more weather stations. And all this should finally allow you to create some models that will provide you forecasts of inflow. So these are the steps that you should consider, let's say, how to find good spots for monitoring. So as time is running out, I'm showing you this map. This is an example of map with the gauging sites and weather stations. And if we proceed further, we also need not only to collect this data, but also to have this data used by the statistical or forecasting models to estimate the flow. So here you may see a rather general structure of the data collection system that we have developed, that allows you to have interface from one side for this agency to provide you the data online so that it feeds your database, and from the other side to have the data that arrives from automated, say, weather stations, automated gauging sites, to get this data and put it to your database online. Apart from that, there is also one block that is a forecasting system that analyzes all these inputs, also gets the data from forecasts of weather, let's say temperature and precipitation, and this forecasting system provides you the estimation of the flow. And one part of the system is creating, let's say, interface that is easy to use by people from different fields, so they are provided with passwords to access the data they need. And finally, if we proceed even further, let's say the construction stage, this system, as soon as it starts working with these automated stations, it makes it quite easy to also integrate some monitoring data, and also what becomes important is not only, let's say, forecasting, but also notifying people about what are the observed parameters, and also alarm system, which allows you to set some expected range for each of parameters for which you collect the data. And if the new value that has arrived is out of expected range, then you have some alarms triggered and some people are notified automatically. So I realized that the topic covered is very general and very hard to cover in such in just one presentation, but if you have any further questions, this is my email. Once again, thank you for attention, and see you on the next in-person event.
Well, thank you to all presenters for their contribution. After having heard all the interesting presentation, let me address a few participants that have put in some questions. And the topics that I selected are basically of two kinds. The first one is the challenge of integrating different renewable energy systems. And the other one is on planning models. So on the first subject, which is definitely the trend we are hearing now from many of these congresses, that the future is in integrating renewables with hydro as the main enabler. There is a question from Mei Jinhong regarding the possibility of increasing the frequency of stopping and starting hydro in an energy system composed by renewables. I would ask Mei Jinhong to ask their question, which I think is directed to either Mr. Sterle or Mr. Horo.
You cannot ask the question directly. You just have to ask the guys to answer it.
Okay, so the question is from a chat between Pravin Karki and was commented by Mei Jinhong, saying that hydro is designed, has been traditionally designed to start and stop operation at not very frequent intervals. In the future, that may be different. Who wants to comment on that, taking into consideration the important role of hydro inertia in a complex system? Maybe Sebastian Sterle want to address this question?
Yes, certainly. Thank you very much, Alessandro. So, of course, it's true that many hydropower projects in the past, from a couple of decades ago, were designed to provide base load power, not necessarily to do load following. But hydro can do load following, and this has been happening more and more as well as turbine technology has progressed and as the importance of load following has increased. So, for example, pumped hydropower stations, which are ubiquitous in certain regions in Europe, in Australia, for example, can do load following on very short timescales, can react very fast to grid imbalances. In many countries, whenever there are problems with grid imbalances, hydro is the first recourse, followed by gas power plants and others if necessary. So definitely some old hydropower plants were not designed for load following and would need refurbishment in order to do that at the necessary timescales and help integrate solar and wind power. But modern hydropower can do this to a large extent. And this is something that should obviously be taken into account when planning any future hydropower projects, that what should be the flexibility necessary and required from this project. And projects should also be valued in terms of how much flexibility they can provide in that regard.
Thank you. Julien Hourou, you want to comment on this point?
Sure, just very briefly. Yeah, in the model results I showed, the plant was only being turned off and on and off to respond to solar at most once or twice a day, typically just once. So I wouldn't say it wouldn't add too strenuous requirements, I would say.
Good. Continuing on this subject, on this topic, there is a question from Lasse Goodman, directed again to Sebastian Sterl. It's quite an indirect question. I don't know if somebody else wants to address. I mean, she was referring to the ambitious program in the UK of providing electricity to all houses by renewable energy with a very ambitious schedule. And she's asking if that is considered feasible in the experience. Again, maybe Julien first and then Sebastian.
Well, yeah, I mean, you know, our Future Dance project is currently looking at systems in West, East Africa, the Middle East, and Myanmar. So we haven't looked at the UK. Obviously, in the UK, we have much less. We have almost very little hydropower, but there's, you know, the flexibility comes from other systems like gas or others. But yeah, so I can't. I mean, since it's not directly related to hydropower, I don't want to talk about this too long.
Okay, Sebastian.
Okay. Yes, thank you very much for the question, Lucy. So, I mean, in the first question should be, how do we interpret this target, providing electricity from wind to all UK homes by 2030? I guess the way I would interpret that is to mean that, let's say, roughly the share in electricity demand that comes from residential homes, that should be the penetration of wind power in the electricity mix by 2030. That's how I would interpret that target. Obviously, that is quite an ambitious target. But it's good to show a roadmap like that for policy making. The Paris Agreement's 1.5 degree Celsius target is also extremely ambitious, but it shows a roadmap and it gives a concrete target to work towards. So I think the way of getting there is maybe more important than whether you reach that exact number in 2030 or not. So the journey is the goal, so to speak. You mentioned three possibilities for helping to balance the grid, which are pumped hydro, batteries, and green hydrogen. So in terms of readiness, technology readiness, the order is firstly pumped hydro, which as Julia mentioned, there is pumped hydro in the UK. But it's relatively limited in terms of installed capacity, and the share of hydropower overall from pump storage, from run-of-river, from reservoir hydropower is relatively limited in the UK. This is obviously something that can help a lot for doing the first steps in helping a higher wind power penetration, but to really get to such ambitious targets by 2030, batteries, which are, let's say, second place in terms of market readiness, will probably play a big role. More and more battery storage deployment now happening across Europe with strongly decreasing costs. Green hydrogen, something that looks promising, but is still extremely uncertain in terms of price and efficiency.
Thank you, Sebastian. Let me go to the second topic, which has been planning models. We heard very good different perspective on those. There is an announcement from one of the participants, Thomas Hugh, that there is a session in session 9 on environment. There is more on planning models, and he's suggesting if not organizing a forum on that. I leave it to the participant to join that. Then there is a question from Tim Ivanov to Mr. Busher, asking what assumptions are made in this model evals for probabilistic approach. How you can take into account probability in evals?
Yeah, we use different discount amounts for calculation of during the calculation of economical analysis. And energy calculations. So we use basically some percentage amounts for increasing or reducing the economical analysis or energy production. So the probabilistic analyses are just at this stage in evals.
Okay, we are there to the conclusion of this session. I just wanted to ask a final question to Mr. Becher. Your model is very comprehensive and takes into consideration the extensive experience of firms like Coyne-Bellier, Tractebel, Lemaier. So are you considering using that system to assess the contingencies to be allocated to a project, which is always a big deal? I mean, you have a lot of uncertainties and you have to price contingencies, to quote contingencies. That something that the model can help doing.
I didn't get your question exactly.
When you make a cost estimate of a project, you get to a figure, but you still have uncertainty. So you say this will be 100 plus or minus 20 or so. Does your model help in quantifying that?
Yeah, we use a unit cost database, which is derived from, say, expressions, and it can be applied all around the world. So we also calculate BOQs based on 3D models for each structure. So at the end, for each project layout, we have detailed BOQs, bill of quantities, and they are converted to prices by using our, say, globally valid cost database. But as you said, there are some contingencies for each element or structure. And these are also calculated within evals. For each structure type, we have some different amount of civil cost contingencies or mechanical cost contingencies, or for electrical parts. So these depends on the element type and the layout of the, say, project.
Okay, let me conclude by thanking also Ms. Becker and Mr. Pinto for their presentations, which cover two important elements. And with that, I would close this session and thank you all very much.